morning or good evening, depending on where you're at in the world. I just want to, again, thank you for joining today's webinar, Optimized Renewable Integration through MicroGrids, brought to you by Landmark International. Just a couple housekeeping things. All questions will be answered at the end of the presentation. And if you'd like to ask a question, you can use the question box on the right-hand side of your screen. Just please note that this presentation will be recorded, and the recording will be posted to our website, so we'll be sure to send out that link following today's webinar. We are top of the hour, so I would like to introduce today's speaker, Sun Grun, who is a consultant as well as a Landmark International Ambassador.
Thank you very much for that introduction. So in this webinar, I will be talking about small-scale renewable energy, such as solar or wind power, and how to integrate them in microgrids. A microgrid is a localized grouping of electricity generation, energy storage, and electric loads connected by a small electric network, usually using low voltage AC. Such a microgrid could operate either connected to a central/national grid or could be completely separate. In any case, the microgrid can function autonomously. So this is the agenda for today's webinar. I will start with the application of isolated island grids, and then continue with the application of uninterruptible power supply, which is one way to use microgrids that are connected to a central or national grid. After that, I will introduce you to power line communication, which is very useful in microgrids. Finally, I will say a bit about the Landmark advantage in this context and give examples how such open systems can help optimize microgrids. The two main applications of microgrids have one thing in common. Both they normally rely on diesel power today. Because of that, microgrids are often optimal places to integrate renewable energy, as you will see. This is an example of two diesel gensets, or generator sets to use the long name, each rated about 40 kilowatts. At half load, such a genset consumes 6 liters of fuel per hour. With Swedish fuel prices, it means that only the fuel cost corresponds to about €0.5 per kilowatt hour electricity generated. If you count the total costs, it's even more expensive. €1 per kilowatt hour is not unusual on remote locations. Here I'm visiting an off-grid area in Brazil, where many homes, except the poorest, have a smaller genset like this. The most common type of fuel used for gensets is diesel, but in some cases another fuel like gasoline is used, especially in the smallest gensets. So what you have seen here are two examples of isolated island grids. These don't have to be physical islands. The point is that their power grid is like an island, totally separated. There are a number of problems associated with these island grids, especially if you do them the traditional way. And the traditional way, as you have understood, is using diesel power. It's polluting and expensive, especially if you run the gensets much. Many of those who have gensets on remote locations can actually not afford running them more than a few hours every day. Introducing renewable energy is usually very economical, but it requires investment. Another problem is battery lifetime and toxic contents, because batteries are often used in these systems, and they are not ideal, although we need them. If some users of power are located close together, sharing a small grid has many benefits compared to individual systems, say on every home. But it can be a challenge to do it right, and that is something I'm going to dwell on now a bit. So there are always challenges of sharing things, like if you would be sharing a microgrid with your neighbors in a remote village, for example. How much do you get and when? If it is sharing a microgrid, then it is about the power and energy you can get from the grid. Since these systems usually have a limited capacity, you cannot get everything you want all the time, of course. And who decides that, what you get and when? And also, what if needs grow? Usually, if you have not used electricity before and you have then an opportunity to use electricity, for example, by introducing a microgrid, electricity needs tend to grow. And as you can see here, these two cats, they seem to be very good friends. They share the food in a very nice way. But it's not always that easy to share things in real life. But if you can do it right, there are definitely advantages of doing this. There are also some special characteristics of wind and solar energy that I want to mention. They are often the most economical energy sources in this context, so they are very attractive to use. But they have their challenges too. One is they vary over time. They can vary very quickly. But the nice thing is they often complement each other. So when the wind is blowing, the sun might not be shining, but when wind is not blowing, you probably have the sun. There may also be periods with shortage or abundance in supply. And these factors we must, of course, take into account if we're going to do microgrids with a high share of renewable energy. And in the graph here, you can see the power from the small wind turbine outside the office where I sit now. This is how it varied a few days ago. And as you can see, sometimes you have nothing, and sometimes you run at more than half power in this case, because the rated power of this turbine is 1,000 watts. So to overcome these challenges and solve the problems, good controls is usually what you need. And my main point here is that if you have an integrated control of supply, storage, and demand, this can enable better sharing and utilization of a variable resource. For example, if you at some times have an abundance of, say, wind, with an automatic control system, you could, at those times, turn on loads which you would otherwise not use, and in that way utilize the wind when it's there. And also, a very important point I'd like to raise is that good controls, in my opinion, are able to communicate with different devices from different manufacturers. For example, to integrate complementing technologies. I mean, imagine, for example, if you would go for a microgrid with only technology from one manufacturer. Maybe they work with solar energy, but if you want to integrate wind, it's a very important thing to be able to do this and not be locked into another type of solution which limits you. And also, it's important that the system is open for modifications and expansions, because electricity demand usually will not stay constant. It usually rises. This is an example of a system called Terroc Independent Power, or TIP, which we have developed at our company. Here we see a simplified example of how a modern microgrid can be built. On the left-hand side, you have the electricity generators, which we call the supply side. In the middle, you can see that electricity is, in this case, distributed via an AC bus, and there is also an energy storage in the form of a battery bank. The battery bank would be connected via power electronics, not shown here. On the right-hand side, you have the consumption of electricity, the loads, which we call the demand side. TIP has a distributed control system, and you can see that in this case there are controllers for the wind turbine, for the solar system, for the gensets, and for the energy storage. However, notice that in the upper right-hand corner you also have smart electricity meter and load controllers. All of these devices can be integrated so they together form a control system for the supply, storage, and demand. It is an open system where the control devices have interfaces according to landmark guidelines, and they communicate with a standardized protocol, which can use a variety of media. One very useful way of communicating, especially to meters and loads, is to use the existing power lines, which I will come back to later. By the way, we are in this webinar focusing on the control system, and Landmark works with the controls and the interfaces. However, if you want to do a complete system, and if you want to do it in a modular way, of course you also need to think about other interfaces. For example, how power plants interface with their power to the AC bus. And as I have indicated in this slide, one way to do this and to do the fast load sharing control on the AC bus is to use a principle called droop. It means that frequency variations on the grid determine the power sharing between the units. Also, I should mention that for some of these devices, there are already so-called functional profiles available, for example, for gensets. For other devices, functional profiles are under development, and these functional profiles greatly simplify the integration of components from different manufacturers. And I will come back to that later and show you an example of such functional profile. So far we have talked about remote locations mainly, but I want to point out that power outages can be a problem both in rural areas as well as in cities. This photo is from Kathmandu, where we have discussed projects to handle the situation with frequent power outages in the city. Here we see an example of a traditional UPS system, where UPS stands for uninterruptible power supply. So this is something you might be using in Kathmandu and also in many other locations, of course. On the left-hand side, you have power coming from the grid, and often you also have a genset which you can connect there in case of a power outage. But the genset always has a certain starting time, so to avoid having to run it all the time, the UPS in the center contains a battery or many batteries and power electronics to ensure that the loads on the right-hand side always have proper power supply. But there are some challenges of UPS systems. One is that batteries have a limited capacity. That's why you, as I mentioned, add the gensets. However, gensets typically run on fossil fuel, and we probably all know the problems related to that. It is not only the global warming issue, there are also a number of other problems associated with this. I mean, imagine if you have some kind of crisis in the world and a shortage. This can really then have an impact on your backup power supply if, say, diesel fuel will be scarce and go up in price. Battery lifetime and toxic contents, that is an issue here as well as on the remote locations. But then we come to a special issue which is especially important in places like Kathmandu, where the grid is probably weak or generation capacity is small. Then a traditional UPS system may make the situation worse. And an example is when the power outage is over, then if everyone wants to recharge their batteries in their UPS systems, this creates an even larger load than you had before on the grid. So instead of supporting the grid, these systems can actually bring the grid down again. So the ideal thing to do, I would say, in these situations, is combining grid backup with on-site generation by renewable energy. And as you can see here, some of the reasons I have for claiming this is that it can extend autonomy time and battery life. This is because you then have the renewable energy filling in, so to speak. So you're not all the time discharging the battery, even if you have a power outage. And it reduces or eliminates the dependence on fossil fuel. And I would say these combinations are more attractive the worse the grid is. Because if you never have any power outages, obviously you're not consuming so much fuel today. But if you have many and frequent outages, the owner saves money by saving fuel. And possibly also by net billing or similar incentives for the power you might supply to the grid. And also, the combination we are discussing here can support the grid and thus be a benefit for the entire society, because maybe this will be the crucial technology that helps the grid stay up during difficult times. Here is an example of a system similar in many ways to what you saw before, but here it is a building with backup power and utility net billing. So again, we have the supply side on the left-hand side. But in this case, the system is connected to a central or national grid. So power is coming in from that grid on the left through a meter in this case, and then through a transfer switch. This transfer switch can enable you to connect the genset when the grid is not working. And during the startup time of the genset, you need a battery bank to handle the situation, and that you see at the bottom of the picture. So far, what I have explained is a quite traditional backup power system. But as you can see here, we have some additional items. Here I have shown how you can add a solar PV system, say on the roof of the building, which can feed the AC bus in the building, both during the normal situation when the ordinary grid is working, and during other situations when the grid has failed and when you might run the genset. On the right-hand side, you can see again a smart meter and load controllers. These are not always necessary, but if you want to optimize a system like this, you need to realize that backup capacity costs money. Especially if you're going to do this without using so much fossil fuel, if you don't want to run the genset much, or if you want to eliminate the use of it completely. If you then use smart controls, where you control both supply side and demand side, as well as the energy storage, you can significantly lower the total investment cost, and you can also increase the security of supply, because low priority loads can be disconnected when needed, and the high priority loads then have a better chance of never going down. In these examples I have shown, we have successfully used lawnmower communication, and it can be used via a variety of media. One of them is power lines. And now I want to go into this a bit deeper to explain the characteristics and advantages here of the power line communication. It is one of the forms of control communication standardized in ISO 14908. It's typically used on existing low voltage grid. That is, here in Europe, normally 230 volts if it's single phase, or 400 volts if it's three phase. In other countries, the voltages could be different. This communication does not go through transformers, so it is not something you use for long distance communication. In my experience, it usually works 1 or 200 meters. And there are suitable products available already on the market. So you can do these systems today. We have been doing them for many years. And if the range I mentioned would not be enough, optional repeating is available from Echelon. And this is a unique advantage to be able to do power line repeating with a very proven and reliable technology. Because these are the main points of the power line communication here, that it works reliably. It is not broadband we're talking about, so it's not for high-speed communication. Of course, if you have another media like an Ethernet network available, that is much better. But this is for the places where you don't have that readily available. Also, I want to mention that future connectivity is planned through two initiatives. The first one is called OpenADR, where ADR stands for Automated Demand Response, and also the new initiative Industrial Internet of Things, which you can read about on Echelon's website, for example. I mentioned functional profiles before, and I want to now explain a bit more what that is all about. You can say it's in a way an object-oriented approach to how you control and monitor a device like a generator set, for example. So if you look at it from the control system side, the graph here on the right-hand side is meant to illustrate the external control system interface. So if you would integrate this genset in a control system with other devices, this is the interface for the other devices or monitoring systems to interact with the genset. And the arrows here are all what we call network variables. That is how LonWorks devices normally communicate. And the basic level of standardization here is that LonMark has defined certain standardized network variable types. This makes it very convenient to make different devices from different manufacturers talk to each other, so you can integrate them in a uniform system. But to take this even one step further, the functional profile defines a set of mandatory network variables. And on the left-hand side, you have these mandatory input network variables on top, and then below that, also an optional input network variable. So the left-hand side here is for the input network variables. The right-hand side is for the output network variables. And below that we have configuration properties. So the point of using a functional profile like this, which is used in the industry today, is that if you buy a generator set with a controller today, you integrate that into your system. One day, if you need to replace the generator set and the controller, if the replacement then follows the same functional profile, it simplifies your work very much at that stage. Because then the interface for the new device will be the same as what you had before. One type of advanced controller that is used by us in these systems today is the Eilon Smart Server made by Echelon. And I want to show here how it can be used. In the previous examples, I have shown fairly advanced systems where you have several of these controllers in the same control system. But in a smaller system, maybe you will only have one of these controllers integrating with a few simple load controllers, for example. So on this slide, I have summarized some of the capabilities of the Smart Server and how it can be used in this context. As you can see in the upper left-hand corner, serial communication with the power converter is possible. We have already implemented the communication protocols of a couple of common inverters on the market, because these devices typically have their own proprietary communication protocols. So with this driver, you sort of translate that proprietary communication to open LONWORKS communication. And then you can also use the Ethernet connection in the upper right-hand corner here. It can be for using the built-in web interface or other forms of communication. At the bottom of the device, you have the power supply input, but this is not just the power supply input, it's also one of the communications channels. So power line communication via 100 to 240 volt AC, 50 or 60 hertz, is possible. So you can use it with low voltage networks worldwide. This can be used to communicate, for example, to smart meters and load controllers, as you have seen before. And then the control logic, for example, for the load control, that is something which you can do custom programming of. And it's even possible for different parties here to write their own different software modules and integrate them together in a very nice fashion. And there are also other options here, for example, to use modem, GSM communication, and so on. So this device can, in some of the smaller systems we make, be the only intelligent controller you need, so to speak. The load controllers can be much simpler. So far we have talked very much about the technical aspects of this, but this is of course not the whole picture. And to look at the broad picture for finding a long-term solution, I think that Lonmark's 9 questions are very useful. Now I will not read through all of them, but they are here for you. The first 5 on this page and the remaining 4 on the other page here. I just wanted to point out that although these questions sound very simple and natural, many people tend to forget them. And if you work with the traditional microgrid systems that are available on the market, if you work with some of the large inverter manufacturers, for example, you will find that these solutions don't fulfill many of the questions asked here. So the risk is that if you don't carefully consider these 9 questions, you will be stuck in another system with a proprietary solution which you cannot easily get out of. And here is a practical example of how this has been used. This photo is from the installation of a grid backup system in combination with solar PV in Bolivia. So this system is in the outskirts of the La Paz area on 4,000 meters above sea level. In some parts of La Paz, the grid can sometimes be overloaded and have other problems. But in this house, the light will stay on also during the power outages, because you have a grid backup system of the type I have explained, where you combine renewable energy on site with uninterruptible power supply capability. Above the door here you have the solar PV modules, and inside the building you have the electronics and the battery bank. So now the presentation is soon coming to an end here, and if you have not already understood all of this, I wanted to point out these examples of how such open systems can help optimize microgrids. The first one is avoid being locked to a proprietary solution. With an open system, you are free to make your own decisions in another way. And also, larger amounts of renewable energy can be integrated, which usually improves the economy, because fuel is saved and less need for batteries. This point might need some explanation. What I mean here is that if you have an open system where you are able to integrate more than the devices from one manufacturer, you're also able to integrate new technology. Say if a new wind turbine would be available on the market, which can help you increase the renewable energy penetration. This is easier to integrate if you are working with an open system. And the third point is larger shared systems can be operated. With the controls I've shown before, especially the load control, it's easier to handle the challenges I mentioned of a shared system. So then you can utilize the economy of scale and do village systems or even larger systems, maybe for towns or other mini grids. And the last point here is automatic transfer of data from different types of systems to a database on a central server enables better follow-up and planning. Imagine if you had been working with a proprietary system. Then if that manufacturer provides this service, you can probably log data with their system. But imagine if you want to do this from many different devices on one site, and not only on one site, but also on many other sites. Maybe you want to log data from wind measurement systems, from other measurement systems, before you, say, want to electrify an unelectrified area in a developing country, and then you want to follow up the power systems you install there, and later on maybe you want to do billing of customers. All of this can, as far as I know, not be done with a proprietary system today. But with an open system, you have the choice to do this. So this is the end of my presentation. Thank you very much for your attention. I hope what I have explained has been clear, but if not, please don't hesitate to ask questions now. I will be happy to answer them as well as I can.
Great. Thank you for the presentation. We do have a couple of questions that came in that I would like to just read off. Can you explain what profiles are in development?
Yes. What I have been working on quite a bit is what you could call a microgeneration profile. It has mainly been intended so far for solar PV and small wind turbines, but it could also be used for other forms of on-site generation. For example, there are now Stirling engines starting to emerge on the market for combined heat and power. So that is one area where development of functional profiles is underway. There's also been work done on an updated metering profile, which I believe already is in place, and that is very useful for the other profiles I mentioned. So I hope that helped answer that question. And also I would like to welcome anyone who is interested in the functional profile development to join the utility task group on Landmark, because that is where this work is done.
Okay, great. Another question, when do you think energy storage will become an economical solution?
Well, I think we have to make a clear distinction here between if we are off-grid or if we are on-grid. For off-grid sites, where the traditional power supply is by diesel power, as I have mentioned, energy storage in batteries is already very economical usually, at least in the smallest systems, say of a number of kilowatts of rated capacity. If you have remote towns with megawatt capacity, you typically have lower generation costs, so there energy storage in batteries might not be so economical. If we then move to the applications where you have the power grid, battery storage is normally not economical for these purposes, because the electric energy you buy from the grid is not so expensive, at least not compared to the remote sites I mentioned. So imagine if you do the lifetime cost calculation of storing energy in a battery. With today's technology, it costs at least 1 Swedish krona to store 1 kilowatt hour in a battery, and that is approximately the price you can buy 1 kilowatt hour from the grid if you're connected. So that is why it doesn't make so much sense there. And when will it become economical? I don't really know if that type of storage will ever become economical. On the other hand, for large grid applications, there are other forms of storage like pumped hydro, which could be economical in many cases already. But if you want to drive your car or operate a remote site, you will find that the energy cost for such uses is much higher, and then 1 krona of storage cost per kilowatt hour is not so much. So I would say if you're waiting for batteries to become very inexpensive so you can use them for anything on the grid, I'm not sure if that is worth waiting for. I think it makes more sense to see where energy storage is already economical today and use it there, but not in a senseless way everywhere. So maybe I should clarify that these microgrids, which I have explained, are probably not for everywhere. They are most economical either if you're off-grid or if you have the grid but you have severe problems with the grid.
Okay. Another question that came in, is there a standard open specification for a microgrid application that can be used by a project manager to require an open system as we discussed, and can that spec be posted on the Lawnmark website?
That's a good question. As far as I know, more work has been done in this field for building automation, because there you have a much higher maturity, if I may say so. Many building owners, they know that they should ask for open systems, and Lawnmark has done quite a bit of work with specifications for this purpose. For microgrids, it is not quite as well prepared. On the other hand, I would say that if you are procuring a hybrid system, you could, I think, pretty much follow what has been done in building automation and specify open systems according to Lawnmark guidelines there. But I'm afraid I don't have a single document to reference to. I think it's a good question, though, where more work should be done.
Okay, and then that brings us to our last question, is what additional support from the industry is needed in order to make an open solution the standard way of installing microgrids?
At this stage, I think the most important thing would be to have more of the big actors in the industry embracing open systems and working more with Lawnmark to make this come true. The technology is already there, standards are there, functional profiles are on the way, and this technology, these standards are used already, as I have mentioned, but only by a handful of the players. Many of the big players in this field are still using old proprietary solutions, and I think it would be very helpful if one or a couple of them showed some leadership here and started working with this standardized way of integrating open systems. A practical thing, if anyone who is listening would like to do something with this, is to adapt the devices you might be manufacturing to work with Lawnmark communication. Another thing to do is to do demonstrational systems where this technology is shown to more potential users.
Great, thank you. And just one last question. What is the most effective way to balance renewables with the grid given their intermittency?
Well, if we're talking about the large grid, I would say the simplest way is to limit the output of the renewables if the output is so high that it can exceed the demand. And that is something which is already possible, for example, with the group control or frequency shift control, as it's also called sometimes. So if there is an abundance in the supply, the frequency normally raises a little bit on the grid, and that frequency rise will then cause the generators with this group control to limit their output. So that can be easily done with solar PV, for example, and that functionality is implemented in many of the commercial inverters on the market. So I think that is the most natural way to start there on the large grid. On the other hand, if you are in special situations, like when you need uninterruptible power supply or on remote locations when power is extremely expensive, then I think it really makes sense to look at energy storage. It could be in the form of batteries, or if you're fortunate enough to have conditions for pumped hydro storage, that is another option. So, was that the last question for today?
At this time, that looks to be the last question, unless anyone has something else they'd like to ask. As a reminder, this recording will be posted to the Landmark website, and we will be emailing out that link. And if there's no other questions, thank you everyone again for joining, and we look forward to any feedback you may have. And thank you to our presenter today.
Thank you also, and as you can see on my last slide, please feel free to contact me via email if you have further questions. So, thank you once again, and